Hello there, and welcome to the Sleepy History Facts channel. Tonight, we are exploring something that might surprise you. The idea that the ancient world was primitive, that the people who came before us were simply waiting for us to arrive and show them how things were supposed to be done. That idea is wrong, profoundly and fascinatingly wrong. The ancient world was full of technologies so sophisticated that some of them took us centuries to rediscover. Some of them we have not fully replicated even now. Some of them we only recently understood after assuming for generations that they could not possibly have existed. Tonight, we are going to spend time with the inventors and the engineers and the craftsmen of the ancient world who built things and discovered things and created things that changed the course of human history and that remind us every time we study them carefully that human intelligence is not a modern invention. It is as old as humanity itself. The people who built the pyramids were not less intelligent than we are. The people who mapped the stars of Babylon were not working with inferior minds. The engineer who designed the Antikythera mechanism was operating at a level of mathematical and mechanical sophistication that would not be matched again for 14 centuries. These are not romantic exaggerations. They are facts supported by archaeology and by science and by the physical objects that the ancient world left behind for us to study and to wonder at. If these quiet journeys through history bring you some peace tonight, I would love it if you liked or subscribed or left a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is settle in. Let your body grow heavy and your breathing slow. And as the night deepens around you, come with me into the workshops and the laboratories and the engineering marvels of the ancient world. Let us begin. The wheel is one of the most important inventions in human history, and it arrived later than you might think. When most people think about ancient technology, the wheel is usually the first thing that comes to mind. It has become a symbol of human ingenuity, something so obvious in retrospect that it seems hard to imagine a world that did not already have it. And yet the wheel was invented only around 5,500 years ago in the region of Mesopotamia, modern-day Iraq, making it considerably more recent than many other human technologies, including agriculture, pottery, and weaving, all of which appeared thousands of years before the wheel did. The reason for this delay is interesting. The wheel is not actually obvious at all. Rollers, logs placed under heavy objects to allow them to be moved, are much more obvious and were used long before the wheel. The conceptual leap from a roller to a wheel on an axle requires understanding that a fixed axle and a rotating wheel can work together as a system in a way that a simple roller does not. The earliest wheels were not used for transportation at all. The oldest known wheel, discovered in Slovenia and dating to around 3,300 years before the Common Era, was a potter's wheel. The application of the wheel to vehicles came slightly later, and the combination of a wheel with a fixed axle to create a wheeled vehicle was one of the most significant engineering breakthroughs in human history. It transformed agriculture, warfare, trade, and communication across the ancient world, and it spread from its origins in the Near East across Asia and Europe with remarkable speed. But here is something that often surprises people. The wheel was invented independently in Mesoamerica as well. The ancient cultures of Mexico created wheeled objects, but used them as toys rather than as practical tools. Wheeled animal toys have been found at archaeological sites in Mexico, dating to around 900 of the Common Era. The cultures that made them did not apply the principle to transportation, partly because the Americas lacked the large domesticated animals that would have made wheeled vehicles practical. Without oxen or horses to pull them, wheeled carts are of limited use. The wheel tells us something important about technology. An invention only becomes useful when the surrounding conditions are ready for it. The wheel was waiting to be invented for as long as human beings existed. It appeared when the conditions that made it valuable were in place. And that pattern of technology waiting for its moment is one that we will encounter again and again tonight. Writing was invented not to record history or tell stories, but to count things. The invention of writing is one of the most consequential technological developments in human history, and it happened in a way that is much less romantic than most people expect. Writing was not invented by poets or priests or philosophers. It was invented by accountants. The earliest known writing system, cuneiform, appeared in Mesopotamia around 5,300 years ago, and the earliest cuneiform tablets are not records of myths or prayers or royal proclamations. They are inventory lists. They record how many jars of grain or oil were received from which farms, and how many were distributed to which workers. They are bureaucratic documents, administrative records, the ancient equivalent of a spreadsheet. The reason writing appeared when it did is that the early Sumerian city-states had grown large enough that the administrative complexity of managing them exceeded what human memory could reliably handle. When you are managing the agricultural output of a large territory and distributing rations to hundreds of workers and tracking the movement of goods across a complex trade network, you need a way to record information that does not depend on any individual person remembering it correctly. Writing solved that problem. Over time, it was extended to other purposes, to the recording of law, to the telling of stories, to the preservation of religious knowledge, to the writing of letters. But its origins were entirely practical and entirely commercial. Egyptian hieroglyphs appeared slightly later than Sumerian cuneiform and were similarly practical in their earliest applications. Chinese writing appeared around 3,200 years ago, initially on oracle bones used in divination, but quickly extended to administrative and literary purposes. The invention of writing independently in at least 3 separate parts of the world suggests that it was not a lucky accident, but an almost inevitable response to a specific set of social and economic conditions. When a society becomes complex enough that it needs to record and transmit information beyond what human memory can reliably store, writing tends to appear. The surprise is not that writing was invented. The surprise is that it took so long. Human beings had been using language for at least 50,000 years before anyone thought to write it down. And when they did, the first thing they wrote was a list of things they owned, which is both entirely understandable and somehow very human. Roman concrete was so good that we still cannot fully understand how they made it. Modern concrete is one of the most widely used building materials in the world. It is strong and versatile and relatively cheap to produce. It is also not as durable as the concrete the Romans made 2,000 years ago. Roman structures built from opus caementicium, Roman concrete, are still standing after 2,000 years in conditions that would have destroyed modern concrete centuries ago. The seawalls and harbour structures built by Roman engineers are still largely intact after 2,000 years of exposure to seawater, while modern concrete seawalls typically show significant deterioration within 50 years. The reason for this difference was only understood relatively recently, when scientists studied samples of Roman marine concrete and discovered something remarkable. Roman concrete actually becomes stronger over time. Modern concrete weakens when seawater penetrates it because the salt water reacts with the calcium silicate hydrate that gives modern concrete its strength and degrades it. Roman concrete does the opposite. The seawater that penetrates Roman harbour concrete reacts with the volcanic ash called pozzolana that was the key ingredient in the Roman. Mix and forms new mineral crystals called tobermorite that fill in the microscopic gaps in the concrete and actually make the structure more solid over time rather than less. The Romans discovered this property of volcanic ash empirically through experimentation and experience without knowing the chemistry that explained it. They knew it worked. They did not know why. The why had to wait for modern materials science. The pozzolana they used came from volcanic deposits near Rome that are not available in most other parts of the world, which is one reason the secret of Roman concrete was so difficult to replicate after the fall of the empire. Medieval and later builders who tried to copy Roman structures did not have access to the same volcanic materials, and the alternative cements they used were considerably less durable. Modern engineers studying Roman concrete are now trying to develop new concrete formulas inspired by the Roman approach that might produce structures with similarly extended lifespans. The Romans solved a problem in material science that we are still working on 2,000 years later. That is not a small thing. That is extraordinary. Greek fire was a weapon so terrifying that its formula was kept secret for centuries and then lost forever. In the 7th century of the Common Era, the Byzantine Empire, the eastern successor to the Roman Empire, found itself under severe military pressure from the rapidly expanding Arab forces that had conquered much of the Middle East. The Arab fleet was formidable, and the Byzantine navy was struggling to match it. And then, a Syrian engineer named Callinicus presented the Byzantine emperor with a weapon unlike anything that had been used in naval warfare before. Greek fire was an incendiary substance that burned on water, not just in contact with water, but on top of it. A substance that could not be extinguished by water, and that in fact burned more fiercely when water was applied. It was projected from siphons mounted on Byzantine warships in a continuous stream of liquid fire that set enemy vessels alight in a way that no conventional defense could stop. Its first major use was against the Arab fleet besieging Constantinople in 678 of the Common Era, and its effect was devastating. The Arab fleet was destroyed, and Constantinople was saved. Greek fire was used in multiple subsequent engagements, and its reputation spread across the medieval world as one of the most terrifying weapons in existence. The formula for Greek fire was one of the most closely guarded secrets in Byzantine history. It was known to only a small number of people and was never written down in a form that has survived. What we know about its composition comes from the descriptions of people who witnessed its effects and from the attempts of Byzantine scholars to describe it without revealing how to make it. Modern chemists and historians have proposed various formulas that might produce something with the properties attributed to Greek fire. The most widely accepted theory is that it contained quicklime, naphtha or crude petroleum, and possibly sulfur and pine resin. The quicklime would react violently with water and could explain why the substance ignited more fiercely when water was applied. But no modern reconstruction has been confirmed, as the original formula and the secret of Greek fire remains genuinely lost. The Byzantines kept it so well that they kept it from us too. The weapon that saved Constantinople and altered the course of medieval history is now only a description of effects with no surviving explanation of causes. One of the most effective military technologies ever created vanished from the world as completely as if it had never existed, because the people who knew how to make it were too careful about keeping the secret and then ran out of time to pass it on. The Antikythera mechanism was a computer built 2,000 years before computers were supposed to exist. In 1901, sponge divers working off the Greek island of Antikythera discovered the wreck of an ancient Roman ship that had sunk around 60 to 80 years before the Common Era. Among the objects recovered from the wreck was a corroded lump of bronze that initially attracted little attention. Over the following decades, as the corrosion was carefully removed and the object was studied more closely, it became clear that this was one of the most extraordinary artifacts ever recovered from the ancient world. The Antikythera mechanism was a mechanical computer. It consisted of at least 30 bronze gears of varying sizes, arranged in a system of extraordinary complexity that could calculate and display the positions of the sun and moon, predict solar and lunar eclipses, track the 4-year cycle of the Olympic Games, and model the irregular orbit of the moon using a system of 2 interlocking gears that replicated with remarkable accuracy the mathematical relationship described by the astronomer Hipparchus to account for the varying speed of the moon in its orbit. This last feature is particularly astonishing. The differential gear mechanism that achieves it was not thought to have been invented until the 16th century of the Common Era. The Antikythera mechanism used it 2,000 years earlier. The device was operated by turning a hand crank that advanced the gears and moved the display pointers to show the current positions of the celestial bodies and to predict future astronomical events. It was in effect a mechanical model of the solar system of an accuracy and sophistication that would not be matched until the astronomical clocks of medieval Europe 1,000 years after it was made. The inscription on the back of the device suggests it may have been used for calendrical and navigational purposes, as well as for the display of astronomical knowledge. We do not know who made it. We do not know exactly where it was made, though Rhodes is the most likely candidate based on the astronomical parameters it uses. We do not know how many similar devices existed, or whether this one was unique. We know only that it existed, that it was recovered from the sea after 2,000 years, and that it rewrote our understanding of what ancient technology was capable of in a way that has not stopped reverberating through scholarship since the moment its true nature was recognized. The ancient Greeks built a computer. Then they forgot how, and we found it at the bottom of the sea. Roman underfloor heating was so effective that some versions of it are still in use today. If you have ever visited a country house in Britain or Europe with underfloor heating, you have experienced something that the Romans perfected 2,000 years ago. The hypocaust system, from the Greek words for under and burn, was a form of central heating used in Roman baths, wealthy private homes, and some public buildings that worked by circulating hot air beneath the floor and through hollow spaces in the walls. The floor of a room with a hypocaust was raised on small pillars of brick or tile called pilae, creating a space of around 60 centimeters beneath the floor surface through which hot air from a furnace could circulate. The walls of the room were lined with hollow ceramic box tiles that allowed the hot air to continue rising through the wall and out through vents near the ceiling. The effect was a room that was heated from below and from the sides simultaneously in a way that distributed warmth far more evenly and efficiently than a central hearth or an open fire could achieve. The floor surface itself became a radiant heating element, similar in principle to the underfloor heating systems installed in modern homes. The Romans were experienced enough with this system to know that the floor directly above the furnace got too hot to walk on comfortably with bare feet. and that bath visitors needed to wear wooden-soled sandals in the hottest rooms. The hippocaust required a continuous supply of fuel to maintain temperature and a slave or worker to tend the furnace and keep the fire going through the hours of operation. In private homes, the fuel consumption was substantial, and the hippocaust was therefore primarily a luxury of the wealthy. In the great public baths of Rome and across the empire, the scale of the operation was considerable, with large banks of furnaces heating water for the pools and hot air for the heated rooms simultaneously. When the Roman Empire declined and fell, the hippocaust largely fell out of use in Europe, and the technology of underfloor heating was effectively lost for over 1,000 years. It was reinvented in the 20th century using electric elements or hot water pipes rather than hot air, but the fundamental principle was the same one that a Roman engineer had perfected 2 millennia earlier. When you walk across a warm floor on a cold morning, you are enjoying a comfort that a Roman citizen would have found entirely familiar. The Baghdad Battery is one of the most debated objects in the history of ancient technology. In 1938, a German archaeologist named Wilhelm Koenig, working at a site near the city of Baghdad in modern Iraq, discovered a small clay jar containing a copper cylinder and an iron rod. The jar dated to around 200 years before the Common Era and had a composition that, Koenig argued, might allow it to function as a galvanic cell, in other words, as a simple electric battery. If the jar were filled with an acidic liquid, such as vinegar or wine, the combination of the copper cylinder and the iron rod would produce a small but measurable electric current. Modern experiments have confirmed that a replica of the Baghdad Battery, filled with grape juice or vinegar, does indeed produce a voltage of approximately 1 volt. This is enough to perform very simple electrochemical processes, such as the electroplating of a thin layer of metal onto another metal surface. The discovery generated enormous excitement and considerable controversy. If the ancients had electric batteries, what did they use them for? Some researchers proposed that they were used for electroplating, applying thin layers of gold or silver to cheaper metals in a way that was indistinguishable from solid gold or silver objects. This would have been a commercially valuable process and would explain why a device capable of producing electric current might have existed in an ancient trading city. The controversy around the Baghdad Battery is genuine and ongoing. Many archaeologists argue that the object was simply a storage jar for a papyrus scroll or some other organic material, and that the metal components have an entirely mundane explanation. The electroplating theory, while intriguing, lacks direct evidence. No ancient texts describe the use of electric current. No other objects have been found that show clear evidence of ancient electroplating that could not have been achieved by other methods. What the Baghdad Battery tells us with certainty is that the ancient world produced objects that have properties we did not expect them to have, and that our understanding of what the ancients knew and could do is still incomplete. Whether it was a battery or not, it is a reminder to hold our assumptions lightly when we are thinking about the capabilities of the ancient world. Ancient Egyptian surgery was remarkably advanced and remarkably practical. The Edwin Smith Papyrus, named after the American Egyptologist who purchased it in 1862 and dating to around 1600 years before the Common Era, though probably based on sources 1,000 years older than that, is one of the most astonishing medical documents in the history of the ancient world. It contains detailed descriptions of 48 surgical cases covering injuries to the head, neck, arms and chest, with a clinical precision that feels remarkably modern. Each case is presented in a consistent format. First, the title of the case, then the examination procedure and findings, then the diagnosis, expressed in one of three forms: an ailment which I will treat, an ailment with which I will contend, or an ailment not to be treated. This third category represents cases that the Egyptian surgeon judged as beyond help, and the willingness to make that judgment and communicate it clearly reflects a pragmatic approach to medicine that is recognizable to anyone familiar with modern triage. The papyrus describes surgical procedures for closing wounds with sutures, the treatment of skull fractures with careful examination of the brain, the management of dislocated shoulders and broken bones, the use of adhesive strips to close wounds, and the observation that certain head injuries produce specific effects in other parts of the body. That last observation is particularly significant. The Edwin Smith Papyrus contains what may be the earliest recorded description of the connection between brain injury and physical effects elsewhere in the body, a relationship that would not be systematically understood for centuries. Egyptian surgeons also performed dental work as evidenced by skeletal remains showing evidence of tooth extraction and the drilling of teeth to drain abscesses. They used willow bark, which contained salicylic acid, the active ingredient in aspirin, as a pain reliever. They used honey as an antibacterial wound dressing, a practice that modern medicine has rediscovered and validated. The gap between ancient Egyptian medicine and the magic and prayer that popular imagination associates with ancient healing is enormous. The Edwin Smith Papyrus is a clinical document. It is rational, systematic, and based on direct observation. It represents a tradition of medical practice that was genuinely sophisticated 3,500 years ago. The invention of glass changed the ancient world in ways that are still changing ours. Glass appears in the archaeological record for the first time around 3,500 years before the Common Era, in the form of glazed ceramic objects and glass beads produced in Egypt and Mesopotamia. The discovery of glassmaking was almost certainly accidental. The conditions required to produce glass, very high temperatures applied to sand containing silica, occur naturally in lightning strikes and volcanic activity, and can occur accidentally in pottery kilns when sand is present in or near the fire. Someone at some point noticed the glassy material produced and began experimenting with how to make it deliberately. The earliest glass objects were solid, cast in molds and ground to shape after cooling. The ability to blow glass, to produce hollow glass vessels, was not developed until around the 1st century before the Common Era, when glassblowers in the region of Syria discovered that molten glass could be inflated on the end of a hollow rod to produce a glass bubble that could be shaped while still hot. This single discovery transformed glassmaking from a luxury craft, producing expensive solid objects for the wealthy, into a medium capable of producing containers of all kinds quickly and relatively cheaply. The glass bottle and the glass window that we take entirely for granted were radical innovations that changed how food and liquids were stored and transported, and how buildings admitted light while excluding weather. The Romans were enthusiastic glassmakers, and Roman glass of the 1st and 2nd centuries of the Common Era shows a level of technical sophistication in its coloring and its shaping that was not equaled in Europe for over 1,000 years after the fall of the empire. The Lycurgus cup, a Roman glass object from the 4th century of the Common Era now in the British Museum, is made of a glass that appears green in reflected light and red when light shines through it. This dichroic effect is produced by nanoparticles of gold and silver dispersed through the glass matrix at concentrations and in particle sizes that give the glass its remarkable optical properties. The Romans achieved this effect without knowing the science behind it. The nanotechnology that explains the Lycurgus cup was not understood until the 20th century. The Romans were accidentally working at the nanoscale 2,000 years before nanotechnology existed as a concept. The aqueducts of Rome represented engineering so precise that errors of a fraction of a degree would have stopped them working. We have already spent time with Roman aqueducts in the context of Roman civilization, but they deserve further attention here as technical achievements because the engineering required to build them was of a precision and sophistication that genuinely astonishes modern engineers who study them. An aqueduct works by gravity. Water flows downhill from its source to its destination along a channel built to a precise gradient that is steep enough to keep the water moving, but not so steep that the flow becomes turbulent and the channel erodes. The ideal gradient for a Roman aqueduct channel was approximately 1 in 3,000, meaning a drop of 1 meter for every 3,000 meters of horizontal distance. Over a total channel length that might be 50 or 60 kilometers, this means a total drop of only around 20 meters from source to destination. Achieving this gradient consistently over such a long distance, through tunnels and across valleys on arched bridges and around hillsides and through varying geology, required surveying instruments and techniques of remarkable accuracy. The Roman surveyor's primary instrument was called a groma, a device consisting of 2 horizontal crossbars mounted on a vertical staff from which plumb lines were hung to establish true vertical. With the groma and the chorobates, a form of spirit level, Roman surveyors achieved alignment and gradient accuracy that allowed their aqueducts to function perfectly over distances that modern engineers find impressive. The Aqua Claudia, completed in 52 of the Common Era under the Emperor Claudius, brought water from springs in the Anio Valley 69 kilometers to Rome, along a channel that maintained its gradient so precisely that the water arrived with exactly the pressure and flow needed to supply the city's fountains and baths and private connections. The longest aqueduct in the Roman world was in the province of Carthage in North Africa. It ran for 132 kilometers and supplied the city of Carthage with water from the springs of Zagawan in the mountains to the south. The survey work required to plan such a structure, to identify a source high enough to supply a distant city, to find a route of manageable gradient through complex terrain, and to construct the channel to the accuracy needed for it to work, represents engineering at a level that demands respect, regardless of the era in which it was achieved. Damascus steel was a metal so extraordinary that metallurgists still argue about its secrets. For several centuries, from roughly 300 to 1700 of the Common Era, the swordsmiths of Damascus in Syria produced blades of a quality that was unmatched anywhere in the world. Damascus steel blades were famous across the medieval world for 2 properties that seemed almost contradictory. They were extremely hard, able to hold a razor edge that could cut through silk falling through the air, and they were extremely flexible, able to bend without breaking in a way that hard metals normally cannot. The blades also had a distinctive surface pattern of wavy lines and swirls called the Damascus pattern, or the watered steel pattern, that was both beautiful and unmistakable. Crusaders who encountered Damascus steel blades in battle reported their qualities with a mixture of admiration and alarm. European smiths of the medieval period tried to replicate the metal and failed completely. The production of Damascus steel died out around 1750 of the Common Era, when the specific ore sources used by the Damascus smiths were apparently exhausted and the knowledge of how to produce the same properties with different materials was lost with the craftsmen who possessed it. Modern metallurgists studying surviving Damascus steel blades using electron microscopy and other advanced analytical techniques have discovered that the extraordinary properties of the metal result from a microstructure of iron carbide nanowires and carbon nanotubes distributed through the steel in a pattern that gives the blade its unique combination of hardness and flexibility. The Damascus smiths produced carbon nanotubes in their steel without knowing what carbon nanotubes were and without modern chemistry to guide them. They achieved it through a specific combination of ore composition, forging temperature, cooling rate, and repeated folding that produced the nanostructure as an emergent property of the process. Modern attempts to recreate Damascus steel have produced materials with some of the visual characteristics, but none of the structural analyses has confirmed the full microstructure of the original. The Damascus smiths took their most important knowledge with them when the tradition ended, and the nanostructure they created without knowing it existed remains one of the most studied and least fully understood materials in the history of metallurgy. Ancient Chinese gunpowder changed the face of warfare and the shape of the world. Gunpowder was discovered in China around the 9th century of the Common Era by Taoist alchemists who were searching for an elixir of immortality. The discovery was an accident. Alchemists experimenting with mixtures of sulfur, charcoal, and saltpeter in pursuit of a life-extending substance instead created a highly flammable mixture that in the right proportions explodes with considerable force. The fact that their search for the secret of eternal life produced instead the secret of more efficient killing is one of the great ironies of the history of technology. The Chinese military was quick to recognize the potential of the new material. The earliest military application was fire arrows, arrows with incendiary packets of gunpowder attached that produced fire and smoke on impact. These were followed by firebombs, containers of gunpowder that were thrown or catapulted at enemy positions. Then came the fire lance, a tube of bamboo packed with gunpowder that produced a burst of flame and smoke when the gunpowder was ignited. The fire lance is the ancestor of the firearm. The transition from a device that produces flame to one that projects a projectile required only the understanding that the expanding gases produced by burning gunpowder in a confined tube could propel an object out of the open end with considerable force. Chinese engineers made that transition around the 12th century of the Common Era, and the first firearms, crude metal tubes firing stone or metal balls, appeared in China at roughly the same time that the knowledge of gunpowder itself was reaching the Islamic world and then Europe along the Silk Road. The European adoption of gunpowder weapons transformed medieval warfare in ways so profound that the entire social structure of medieval Europe was eventually affected. The castle, the armored knight, the feudal system that depended on them were all rendered obsolete over the following centuries by weapons that gunpowder made possible. The Taoist alchemists searching for immortality found something that changed the world instead, and not in the direction they were hoping for. The Inca built an empire across the Andes without the wheel and without writing. The Inca Empire at its height in the 15th and early 16th centuries of the Common Era was the largest empire in the pre-Columbian Americas and one of the largest in the world at that time. It stretched 4,000 kilometers along the western coast of South America, from modern Colombia in the north to central Chile in the south, and governed a population of around 12 million people across an extraordinarily varied terrain of high mountains, coastal desert, and tropical rainforest. What makes the Inca Empire particularly remarkable from a technological perspective is that it was built and administered without two of the technologies that most other complex civilizations had relied upon. The Inca did not use the wheel for practical purposes, and they did not have a writing system in the conventional sense. Their system of information storage and transmission was instead the quipu, a device consisting of a series of colored strings with knots tied at specific positions that encoded numerical and possibly narrative information in a form that trained administrators could read and interpret. The quipu allowed the Inca state to maintain census records, manage tribute obligations, record agricultural data, and transmit administrative information across the empire without writing a single word on a single page. The road network the Inca built to bind their empire together was one of the engineering wonders of the pre-Columbian world. Approximately 40,000 kilometers of road crossed some of the most challenging terrain on Earth, including passes in the Andes at altitudes of over 4,500 meters. The roads were paved with stone in many sections and included drainage systems to prevent erosion. Where rivers or chasms interrupted the route, the Inca built suspension bridges of woven grass fiber, strong enough to carry laden llamas and marching armies. These grass fiber suspension bridges were rebuilt annually by the communities responsible for their maintenance under the Mita labor system. The longest of them spanned over 45 meters. The principle of the suspension bridge, using the tensile strength of fiber or cable to support a deck spanning a gap, is the same principle used in modern suspension bridges. The Inca implemented it in grass with a precision and a reliability that allowed their road network to function for generations in one of the most demanding environments on Earth. Ancient Greek automata were mechanical devices that could move and perform without human intervention. When we think of robots and automata, we tend to think of them as products of the modern, or at least the early modern world. The mechanical toys of the Renaissance, the automata of the 18th century, the industrial robots of the 20th. But the ancient Greeks were building self-moving mechanical devices at least 2,000 years before any of these. The inventor and mathematician Hero of Alexandria, who lived in the 1st century of the Common Era, designed and built a series of mechanical devices that are described in his surviving texts with a precision that makes clear he was writing about things he had actually made. Among his inventions was an automated theatre in which mechanical figures performed a 10-minute play powered by a descending weight that drove a system of ropes and pulleys and gears. The figures moved, turned, performed actions appropriate to the narrative, and interacted with mechanical props in what was essentially a programmable mechanical performance running from a stored program encoded in the arrangement of the ropes. Hero also built coin-operated machines. Inserting a coin into a slot caused a measured amount of holy water to be dispensed from a sacred vessel in a temple. The world's first vending machine, operating in Alexandria 2,000 years before anyone built another one. He built a self-powered cart that could travel a predetermined route using a weight-driven mechanism and a programmable string arrangement that steered the cart by engaging the wheels at specific intervals. He designed a steam-powered sphere that rotated when steam was applied to it, a device that contained the principle of the steam engine without anyone recognizing or applying that principle for another 15 centuries. Hero's work was not unique. Archimedes before him had designed mechanical devices of remarkable complexity, including a mechanical sphere that modeled the movements of the sun, moon, and planets. Ctesibius of Alexandria had invented the water clock, the force pump, and the pipe organ. The intellectual tradition of ancient Alexandria was genuinely engaged with the practical application of mechanical principles in ways that produced devices of surprising sophistication. What prevented these inventions from transforming the ancient world in the way that similar inventions transformed the modern one is a question that historians of technology still debate. Part of the answer is that the ancient world had abundant enslaved labor, which reduced the economic pressure to develop labor-saving machines. Part of the answer is that the institutional support for applied technology was less developed than the support for theoretical inquiry. But part of the answer is simply that the time was not ready, and that the best inventions sometimes have to wait for the world to catch up with them. Archimedes was the greatest engineer the ancient world produced, and he barely scratched the surface of what was possible. Archimedes of Syracuse lived from approximately 287 to 212 years before the Common Era, and in that time produced a body of mathematical and engineering work that was so far ahead of his contemporaries that some of it was not fully understood. Until the Renaissance, his mathematical contributions included the first accurate calculation of pi, the discovery of a method for calculating the area under a curve that anticipated the calculus of Newton and Leibniz by nearly 2,000 years, and a proof of the relationship between the volume of a sphere and its circumscribing cylinder that he considered his greatest achievement and asked to have commemorated on. His tomb. His engineering achievements were equally remarkable. The Archimedes screw, a device for raising water using a helix inside a cylinder, is still used in some parts of the world today for irrigation and flood control. The compound pulley systems he designed allowed very large weights to be moved by a single person applying moderate force. He reportedly demonstrated this to King Hiero of Syracuse by single-handedly launching a large ship from the shore using a system of compound pulleys, something that would normally have required hundreds of men. During the Roman siege of Syracuse in 213 before the Common Era, Archimedes designed the defensive weapons that kept the Roman army at bay for nearly 2 years, despite their overwhelming numerical superiority. These included siege engines that could drop large stones on attacking ships, cranes that could reach out over the city walls and overturn attacking vessels, and possibly arrangements of mirrors that could focus sunlight to set attacking ships on fire. Though this last claim is disputed by modern scholars, and the physics of doing so at the distances involved may have been beyond what was achievable. Archimedes was killed by a Roman soldier when Syracuse finally fell, despite orders from the Roman general Marcellus that he was to be taken alive. The story that has come down to us says he was working on a mathematical diagram when the soldier entered and told him to come. He asked the soldier to wait until he had finished his work. The soldier killed him. It is the story of a mind so absorbed in its work that it could not be interrupted even by death. Whether or not it is literally true, it captures something real about what Archimedes was. The printing press was invented in China 500 years before Gutenberg, and in Korea before that. Johannes Gutenberg's invention of the movable type printing press in Europe around 1450 is one of the most celebrated technological breakthroughs in Western history. Its effects on European society were indeed revolutionary, but Gutenberg was not the first person to invent printing. Not by 500 years. Block printing, in which a carved wooden block is inked and pressed onto paper or fabric to transfer an image or text, was practiced in China from at least the 7th century of the Common Era and possibly earlier. The Diamond Sutra, a Buddhist text printed in China in 868 of the Common Era, is the oldest known printed book in the world and was produced using block printing techniques of a quality that indicates a well-established and refined craft tradition. Movable type, in which individual characters can be arranged and rearranged to compose different texts, was invented in China by Bi Sheng around 1040 of the Common Era, 400 years before Gutenberg. Bi Sheng made his movable type from baked clay. Later Chinese printers used wood and then bronze. The technology spread to Korea, where metal movable type was being produced in the 13th century of the Common Era, more than 200 years before Gutenberg. The Jikji, a Korean Buddhist text printed using metal movable type in 1377, is the oldest known book printed with metal movable type still in existence. It predates Gutenberg's Bible by nearly 80 years. Why then did printing not transform East Asian society in the way it transformed European society after Gutenberg? The answer has several components. Chinese and Korean writing systems contain thousands of characters rather than the 26 letters of the Latin alphabet. This means that a movable type system for Chinese or Korean requires thousands of individual type pieces rather than a few hundred. The logistical complexity of managing such a system reduced some of the efficiency advantages of movable type compared with block printing of entire pages. Block printing remained dominant in East Asia, in part because it was better suited to the writing system and to the specific economic and social conditions of those societies. The genius of Gutenberg was not the invention of printing. It was the adaptation of printing technology to the specific conditions of European languages and European markets at a moment when those conditions were ready for the transformation it produced. Ancient astronomy was more precise than its reputation and more consequential than its methods suggest. The popular image of ancient astronomy is of priests staring at the sky and reading omens in the movements of stars and planets for religious or superstitious purposes. The reality was considerably more sophisticated. Ancient astronomers in Babylon, Egypt, India and Greece made systematic observations of the sky over periods of centuries and produced astronomical models of remarkable accuracy that served both practical and theoretical purposes. The Babylonian astronomers of the first millennium before the Common Era had accumulated observational records stretching back centuries and had used this data to develop mathematical models that could predict the positions of the moon and planets and the occurrence of eclipses with a reliability that was genuinely impressive. Their eclipse prediction cycle, the Saros cycle of 18 years and 11 days, identifies the period after which eclipses repeat in a recognizable pattern and was known to the Babylonians by the 7th century before the Common Era. The Greek astronomer Eratosthenes, working in Alexandria in the 3rd century before the Common Era, calculated the circumference of the Earth using nothing more than the angle of the sun's shadow in 2 different cities on the same day and a knowledge of the distance between them. His result was within a few percent of the correct value. Hipparchus, working in the 2nd century before the Common Era, discovered the precession of the equinoxes, the slow wobble of the Earth's axis that causes the position of the stars at any given season to shift very slightly over time. This is an extraordinarily subtle phenomenon that required comparing astronomical observations made centuries apart to detect the tiny change in stellar positions. Aristarchus of Samos, working in the 3rd century before the Common Era, proposed that the Earth revolves around the Sun rather than the Sun around the Earth. He was right. But his heliocentric model was not accepted by most ancient astronomers, and the geocentric model of the universe prevailed for another 18 centuries until Copernicus proposed the heliocentric system again in 1543. The ancient astronomers were working with naked eye observations, with careful record keeping, and with mathematical reasoning of considerable sophistication. Their instruments were simple. Their methods were not. The Delhi iron pillar has not rusted in 1600 years, and science only recently understood why. In the courtyard of the Quwwatul Islam Mosque in Delhi in India stands an iron pillar approximately 7 meters tall and weighing around 6 tons. It was erected around 400 of the Common Era, during the reign of the Gupta Emperor Chandragupta II, and is inscribed with Sanskrit text celebrating the victories of a king whose exact identity is still debated by historians. What makes the Delhi iron pillar extraordinary is not its size or its inscription, but the fact that after 1600 years of exposure to the Delhi climate, including monsoon rain and fluctuating temperatures and high humidity, the pillar shows almost no rust. An iron object of this size exposed to these conditions would normally show severe corrosion after a century or two. The Delhi iron pillar should be a pile of rust. Instead, it stands essentially intact. The explanation for this was determined by Indian metallurgists in 2002, who analyzed samples of the pillar's surface and discovered that it was coated with a thin layer of misoite, a compound of iron, oxygen, and hydrogen that forms a protective patina on the surface and prevents further oxidation. The formation of this protective layer was the result of the specific composition of the iron used, which contained a higher proportion of phosphorus than modern iron, and a lower proportion of sulfur and manganese. This particular combination of impurities encouraged the formation of misoite rather than the conventional iron oxides that we call rust. The ancient Indian smiths who made the pillar did not know about misoite or phosphorus content or oxidation chemistry. They had developed through centuries of empirical practice a method of producing iron of a composition that happened to resist corrosion in the conditions of northern India. They knew the recipe worked, even though they did not know why it worked. The pillar is a monument to the power of empirical knowledge built up through observation and practice without the theoretical framework to explain it, to produce results that theory alone could not have achieved. The ancient Indian ironworkers were better metallurgists in practice than modern material scientists could be in theory alone, and the standing proof of their skill is still standing in Delhi and still not rusting. Ancient paper and what it replaced reveals how transformative the invention really was. Paper was invented in China around the 2nd century before the Common Era, though its use was not widespread until the 1st and 2nd centuries of the Common Era, when improvements in the production process made it cheaper and more practical to produce in large quantities. The traditional attribution of the invention to a court official named Kai Lun around 105 of the Common Era records a significant improvement in the process rather than the original invention. Before paper, writing surfaces in the ancient world included clay tablets, papyrus, parchment made from animal skin, silk, bamboo strips, and wooden tablets. All of these had significant limitations. Clay tablets were heavy and fragile. Papyrus was expensive and available only from Egypt. Parchment required the skin of animals and was very expensive in large quantities. Silk was luxurious but enormously costly. Bamboo and wood were heavy and bulky. Paper solved all of these problems simultaneously. It was light, relatively cheap to produce in large quantities, durable when kept dry, flexible, and capable of holding ink clearly. The adoption of paper in China transformed the administrative capacity of the Chinese state, the accessibility of books and learning, and the speed at which information could be produced and distributed. Paper spread from China along the Silk Road, reaching the Islamic world in the 8th century of the Common Era, after Arab forces captured Chinese papermakers at the Battle of Talas in 751. The Islamic world adopted paper with enthusiasm, and the House of Wisdom in Baghdad became a center of paper-based scholarship that preserved and extended the learning of the ancient world through a period when much of Europe had lost access to it. Paper reached Europe in the 12th century, and its spread there coincided with and facilitated the explosion of learning that would eventually become the Renaissance. The invention of the printing press in Europe in the 15th century would have had far less impact without paper as the medium on which printing was done. Paper and printing together changed the world. Paper was the enabling technology, without which the other could not have had its effect. And paper came from China and took over 1,000 years to reach Europe. What these ancient technologies tell us about the people who made them. We have spent this evening with some of the most extraordinary technical achievements of the ancient world, and what they tell us, collectively, is something important and worth sitting with. The people who made these things were not less intelligent than we are. They were not working in the dark, waiting for the light of modernity to arrive. They were observing the world around them with the same curiosity and the same intelligence that human beings have always brought to the world they inhabit. They were solving problems. Sometimes the same problems we are still working on. Sometimes problems that we have not noticed yet, but that they had already solved in ways we are only now beginning to understand. The Roman concrete that becomes stronger in seawater. The Damascus steel with its carbon nanotubes. The Antikythera mechanism with its differential gear. The Delhi iron pillar with its corrosion-resistant phosphorus composition. All of these represent the application of human intelligence to specific problems in ways that produced solutions of extraordinary quality without the benefit of modern scientific theory to guide the process. They worked empirically. They experimented and observed and refined and improved until they had something that worked, even when they did not fully understand why it worked. And in some cases, what they made was so good that we have not yet surpassed it. The lesson of ancient technology is not that our ancestors were like us, but that humanity has always been like itself, curious, inventive, practical, willing to work for a long time on a problem that seems impossible until the moment it is solved. The Antikythera mechanism was built by a human being sitting at a workbench with bronze and tools, thinking about the movements of the planets. The Roman concrete was mixed by hands that did not know what a chemical bond was, but that understood which combinations worked because they had tried them and observed the results. The Damascus swords were forged by hands that did not know about carbon nanotubes, but that had learned through generations of practice exactly how to fold and heat and cool the metal to produce something of extraordinary quality. These people were us. Different in their world and their knowledge and their understanding of why things work, identical in their capacity to figure out how to make things work anyway. That capacity is the most ancient and the most enduring human technology of all, and it is still in full operation tonight, in every workshop and every laboratory and every mind that is quietly working on a problem whose solution will one day seem obvious to the people who come after. And so, we come gently to the end of our journey through the technologies of the ancient world. We have held a piece of Roman concrete that has been getting stronger for 2,000 years. We have watched a Roman warship project a stream of Greek fire across dark water. We have turned the hand crank of the Antikythera mechanism and watched the gears move, and the pointers show the position of the moon. We have walked across an underfloor heating system that was already old when our own civilization was young. We have held a Damascus blade and felt the edge that was made from nanostructures its maker did not know existed. We have looked up at the Delhi iron pillar and understood that the hands that made it knew something ours forgot. We have stood on an Inca bridge of woven grass over a gorge in the Andes and trusted it because it held generations before us. We have read the Edwin Smith papyrus and recognized the clinical mind behind it. And we have held the Antikythera mechanism and understood that somewhere in the ancient world, a human being sat down and thought about how to build a machine that could model the cosmos, and then built it. The ancient world was not waiting for us to arrive. It was already here, already thinking, already building, already solving problems that we would forget and rediscover and sometimes still have not fully solved. That is humbling. And it is wonderful. If this quiet journey through the ingenuity of the ancient world brought you some peace tonight, I would love it if you liked or subscribed or left a thought below. It helps others find their way here too, one sleepy soul at a time. And if there is still some wakefulness left in you, there should be another calm history waiting on the screen for you now. But for this moment, there is nothing more to follow. Let the ancient workshops fall quiet. Let the furnaces cool and the forge fires die down. Let the gears of the mechanism come to rest. Let your breathing become slow and even and easy. The ancient engineers have done their work for tonight. Sleep well. Good night. The invention of the calendar was one of the most complex technological achievements of the ancient world. We use a calendar every day without thinking about how extraordinarily difficult it was to create one. A calendar requires you to reconcile 3 natural cycles that do not divide evenly into each other. The day, the time it takes the Earth to rotate once on its axis. The month, approximately the time it takes the Moon to complete one orbit of the Earth. And the year, the time it takes the Earth to complete one orbit of the Sun. If these 3 cycles were simple multiples of each other, calendar making would be straightforward. They are not. A year contains approximately 365 and a quarter days. A lunar month contains approximately 29.5 days. 12 lunar months add up to only 354 days, 11 days short of a solar year. If you use a purely lunar calendar, the months gradually drift through the seasons until the month that once began at the spring equinox is starting in winter. If you use a purely solar calendar, you lose the regular rhythm of the lunar cycle that was enormously important for religious and agricultural timing in most ancient societies. The various solutions that different ancient cultures devised to reconcile these conflicting cycles represent genuinely sophisticated mathematical and astronomical work. The Babylonians devised a system of intercalation in which an extra month was added to certain years in a 19-year cycle that kept the lunar and solar calendars in approximate alignment. This metonic cycle, named after the Greek astronomer Meton, who described it in the 5th century before the Common Era, was actually known to the Babylonians several centuries before Meton. The Egyptian civil calendar of 365 days was one of the earliest fixed-length calendars, and its influence on the Julian calendar, introduced by Julius Caesar, is direct and acknowledged. Caesar's calendar reform guided by the Egyptian astronomer Sisigines, introduced the 365-day year with a leap day every 4 years, and created a calendar so accurate for its time that it remained the standard in most of Europe for 1,500 years until the Gregorian reform of 1582 corrected the slight remaining drift by skipping certain leap years. The Gregorian calendar we use today is the product of 3,000 years of astronomical observation and mathematical refinement that began with ancient Babylonian astronomers watching the sky from their ziggurat towers and counting the days between full moons. Ancient Indian mathematics gave the world the number 0 and transformed all calculation. The number 0 is so fundamental to modern mathematics that it is almost impossible to imagine mathematics without it. And yet 0 is an invention. It did not always exist. The ancient Greeks, who were extraordinarily sophisticated mathematicians in many respects, did not have a concept of 0 as a number. They had a concept of nothing as an absence, but not of 0 as a quantity that could be added and subtracted and multiplied and used as a placeholder in a positional number system. The concept of 0 as a number was developed in India, and the earliest known text to treat 0 explicitly as a number with its own mathematical properties is the Brahmasphutta Siddhanta, written by the Indian mathematician Brahmagupta in 628 of the Common Era. Brahmagupta stated rules for arithmetic operations involving 0, including the fact that any number added to 0 equals itself, and any number multiplied by 0 equals 0, in what was the first formal treatment of 0 as a mathematical quantity. The positional number system that goes with the concept of 0, in which the value of a digit depends on its position within a number, was also developed in India and reached the Islamic world in the 8th century of the Common Era, where it was enthusiastically adopted and extended by Islamic mathematicians. It reached Europe in the 12th century through the work of translators and scholars who recognized its enormous practical advantages over the Roman numeral system that Europe had been using. Try doing long division in Roman numerals. Then try it with the positional system. The difference is immediate and overwhelming. The adoption of Indian numerals and the concept of 0 by European mathematics in the medieval period was as significant a technological transfer as any that occurred in the ancient or medieval world. Without 0, we cannot have the mathematics that underlies modern science and engineering. Without the positional number system, we cannot have efficient calculation of any kind. Both came from ancient India. Both transformed the world that received them, and both are so fundamental to how we think about numbers that most people who use them every day have never considered that someone had to invent them. The ancient Egyptians built the pyramids using technology we are still trying to fully understand. We have talked about the pyramids before in the context of Egyptian civilization, but in the context of ancient technology, they deserve a closer look specifically at the engineering problem they represent and at what the solutions to that problem tell us about Egyptian technical capability. The Great Pyramid of Khufu contains approximately 2.3 million stone blocks with an average weight of around 2.5 tons each, and some blocks weighing as much as 80 tons. The base of the pyramid is level to within 2.1 centimeters across its entire perimeter of 900 meters. The 4 sides are aligned to true north, south, east, and west with a deviation of less than 1/10 of a degree. The pyramid was built to this precision in approximately 20 years, which means that an average of around 315 blocks had to be quarried, shaped, transported, and placed every single day for those 20 years. That is about 13 blocks per hour, one block every 4.5 minutes, around the clock. Every day, for 2 decades. How was this achieved? Modern experimental archaeology has demonstrated some of the methods. Copper tools were used for cutting limestone, which is relatively soft. The harder granite used in the interior chambers required pounding stones of dolerite rather than metal tools. Wooden sledges were used to move the blocks on the quarry floor. Water poured in front of the sledges reduced friction dramatically, a technique depicted in ancient Egyptian tomb paintings. Ramps of various kinds were almost certainly used to raise blocks into position as the pyramid rose. The exact nature of those ramps is still debated because no ramp has survived, and the question of how to build a ramp that does not itself become an enormous construction project at the later stages of the pyramid's construction has not been definitively resolved. What the pyramid tells us about Egyptian technology is that the Egyptians had developed a level of organizational capability, administrative sophistication, and practical engineering skill that could mobilize and coordinate a workforce of tens of thousands of people across a project lasting 20 years to produce a result of extraordinary precision. The technology was not supernatural, but it was the product of a civilization that had been developing its engineering knowledge and organizational capacity for many centuries before the first stone was laid, and whose achievement remains impressive no matter how thoroughly modern scholarship explains it. The ancient Persians built underground water channels called qanats that are still in use today. One of the most ingenious hydraulic engineering achievements of the ancient world is one that most people have never heard of. The qanat is a gently sloping underground channel that carries groundwater from an aquifer in the mountains to agricultural land and settlements in the lowlands, using only gravity and the pressure of the water table. The qanat system was developed in the Persian Empire around 3,000 years ago in what is now Iran, and spread across the Islamic world from Spain to China as one of the most effective water management technologies ever created for arid and semi-arid regions. A qanat begins with a mother well sunk at a point where the water table is accessible in the mountain foothills. From the bottom of this well, a tunnel is dug, sloping downhill more gradually than the terrain above, so that the tunnel gradually descends below the water table and allows groundwater to seep in and flow along it. At intervals along the tunnel, vertical shafts are sunk to the surface to provide ventilation for the diggers and access for maintenance. These shafts, visible from the air as a line of circular openings in the desert, are one of the ways qanats can be identified from above. The tunnel can extend for many kilometers, sometimes as much as 50 or 60, and at its lower end delivers a continuous flow of water to the fields and homes at the destination. Because the entire system is underground, the water is protected from evaporation, which would be enormous if the water were carried in open channels across the surface of an arid landscape. The qanat delivers water with remarkable efficiency, precisely because it keeps the water out of the sun. There are approximately 37,000 qanats still functioning in Iran today, some of them thousands of years old. They continue to supply water to farms and villages in exactly the same way they did when they were first built. The qanat is not a museum piece or an archaeological artifact. It is living infrastructure that is still doing the job it was built to do 2,000 years after the hands that built it were buried in the same earth through which it flows. The ancient Cambodian city of Angkor had a water management system of extraordinary sophistication. The city of Angkor, the capital of the Khmer Empire, from approximately the 9th to the 15th centuries of the Common Era, was at its height one of the largest cities in the medieval world, with a population that modern estimates place at around 1 million people. Feeding and supplying that population in a region with a strongly seasonal rainfall pattern, where the monsoon brings enormous quantities of rain for a few months and almost none for the rest of the year, required a water management system of extraordinary sophistication. The Khmer engineers who built Angkor created one of the most elaborate hydraulic networks of the medieval world. Enormous artificial reservoirs, called beres, were constructed to store monsoon water for use during the dry season. The West Beret, the largest, is approximately 8 kilometers long and 2.5 kilometers wide, and could store enough water to irrigate the rice fields around Angkor through months of dry weather. Canals connected the berets to each other and to the moats of the great temple complexes, including Angkor Wat, whose moat is the largest in the world, and to a network of distribution channels that carried water to agricultural land across the region. The entire system was designed to manage water in both directions, storing it during the monsoon and releasing it during the dry season, but also draining it quickly after heavy rain to prevent flooding of the city and the rice fields. The engineering required to design and maintain this system required sophisticated understanding of hydrology and landscape that the Khmer engineers possessed in abundance. Modern analysis using remote sensing technology has revealed the full extent of the Angkor hydraulic network for the first time, and its scale and complexity have genuinely surprised researchers who expected something impressive but found something extraordinary. The collapse of the Khmer Empire in the 15th century has been linked in part to the failure of this water management system, damaged by a combination of overextension, population growth, and the increasingly severe droughts that marked the transition from the medieval warm period to the Little Ice Age. The system that had sustained a city of 1 million people for 5 centuries was ultimately vulnerable to the same climatic forces that every hydraulic civilization has had to negotiate. But while it worked, it was one of the most impressive feats of engineering the medieval world produced. Ancient Polynesian navigation was a technology of the mind as much as the sea. Perhaps the most remarkable navigational achievement of the ancient world is one that left almost no physical artifacts behind, because the technology existed entirely in the minds and bodies of the people who practiced it. The Polynesian people who spread across the Pacific Ocean between. Approximately 1,500 years before the Common Era and 1,000 of the Common Era colonized every habitable island in a vast triangle stretching from Hawaii in the north to New Zealand in the south to Easter Island in the east. This triangle of ocean covers an area of approximately 28 million square kilometers, larger than the entire landmass of Asia. To navigate it reliably across open ocean with no landmarks, in canoes without instruments, to find small islands separated by thousands of kilometers of open water, required a navigational technology of extraordinary sophistication. Polynesian navigators read the ocean and the sky with a precision and a comprehensiveness that allowed them to sail purposefully to specific destinations across distances that European navigators of the same era would not have attempted. They read the stars, knowing the rising and setting points of hundreds of stars, and using this knowledge to maintain direction through the night. They read the swells, the deep ocean swells that propagate across the Pacific from consistent directions for thousands of kilometers, and that can be felt in the movement of the canoe even when they cannot be clearly seen. They read the wind patterns and the cloud formations, and the behavior of birds, and the color and temperature of the water. They read the phosphorescence of the wake and the presence of certain fish species that indicated proximity to land. All of this knowledge was accumulated over generations, encoded in chants and navigation charts made of sticks and shells, and transmitted through apprenticeship and practice from experienced navigators to their students. The European assumption, held for centuries, that Polynesian islands were colonized by accidental voyages of people blown off course, has been thoroughly refuted by both experimental voyages and computer modeling of ocean conditions. Polynesian navigation was not accidental. It was deliberate, skilled, and based on a deep knowledge of the Pacific that represented one of the most sophisticated bodies of navigational knowledge ever accumulated by any culture in any era. The technology existed in human minds and human bodies. It left no bronze gears and no concrete harbors, but it carried people across the largest ocean on Earth and placed them on islands that no other human beings had ever found. The Roman military used technology so advanced, it gave them an advantage for centuries. The success of the Roman military was not simply a matter of courage or discipline, though both were present in abundance. It was also a matter of technology. The Roman legion was equipped and organized as a technological system in which every element worked together to maximize the effectiveness of the individual soldier and the collective force of the unit. The pilum, the Roman heavy javelin, was one of the most cleverly designed weapons in the ancient world. It consisted of a wooden shaft topped by a long, thin iron shank with a hardened pyramidal tip. When thrown, the tip would penetrate an enemy's shield, and the weight of the wooden shaft would cause the javelin to bend downward, dragging the shield down with it and making it difficult or impossible to use. The softness of the iron shank was deliberate. After use, it could not easily be thrown back because the soft iron bent on impact. The design incorporated an understanding of materials and mechanics that produced a weapon optimized for its specific tactical purpose, with a precision that speaks to considerable engineering thought. Roman body armor evolved significantly over the centuries. The lorica segmentata, the articulated iron plate armor most often associated with Roman soldiers in popular culture, was a relatively late development and represented a sophisticated solution to the problem of providing both protection and mobility. Its overlapping horizontal bands of iron plate allowed the upper body to move freely while providing protection against the downward slashing blows that were common in ancient combat. The articulation of the armor was achieved through a system of hooks and hinges and leather straps that required skilled craftsmanship to produce and careful maintenance to keep functional. The Roman siege technology that allowed the army to capture fortified cities was perhaps the most technically sophisticated military technology of the ancient world. The Roman army could build a siege tower that matched the height of any city wall, a battering ram protected by a roofed structure, artillery capable of throwing heavy stones or bolts with considerable accuracy, and an encircling wall that prevented both reinforcement of the besieged city and escape of its inhabitants. At the siege of Jerusalem in 70 of the Common Era, the Roman general Titus built a complete wall encircling the entire city of Jerusalem in only 3 days. The organizational and engineering capability required to achieve that was extraordinary by the standards of any era. The ancient Maya developed a calendar more accurate than the European one in use when they were conquered. The Maya civilization of Mesoamerica developed one of the most sophisticated calendar systems in the ancient world, and their astronomical knowledge accumulated over centuries of careful sky watching produced calculations of extraordinary precision. The Maya tracked the movements of Venus with particular care, and their Venus calendar, which appears in the Dresden Codex, one of the few Maya books to survive the Spanish conquest, predicted the appearance and disappearance of Venus as the morning and evening star with an accuracy that required only a one-day correction every 6,000 years. The Maya also calculated a solar year of 365.242 days, compared with the modern accepted value of 365.2422. The Julian calendar in use in Spain when the conquistadors arrived was less accurate than the Maya solar calendar. The Maya long count calendar, which tracks time in units from individual days up to periods of over 5,000 years, was a sophisticated positional number system applied to timekeeping that allowed the Maya to record dates with precision across spans of thousands of years. The correlation between the Maya long count and the modern calendar has been established with considerable confidence, allowing us to convert Maya dates to our own calendar system and to recognize the extraordinary precision of Maya astronomical records. The destruction of most Maya books by Spanish missionaries, who burned them as works of the devil, represents one of the greatest losses of ancient knowledge in history. The 4 books that survived give us only the faintest glimpse of the astronomical and mathematical tradition that the Maya had developed over centuries. What those 4 books contain is remarkable enough to make the loss of the rest almost painful to contemplate. Ancient China's technological achievements were centuries ahead of the rest of the world across multiple fields. China's contribution to the history of technology is so extensive that a single evening could not do it justice. But some highlights deserve particular attention. Cast iron was produced in China from around the 5th century before the Common Era, roughly 1800 years before cast iron appeared in Europe. The ability to cast iron in molds allowed Chinese craftsmen to produce agricultural tools, cookware, and eventually weapons in quantities and at costs that were not possible with wrought iron or bronze. The drill bit, the wheelbarrow, the fishing reel, the stirrup, the mechanical clock, the cast iron plough, matches, the toothbrush, the suspension bridge, toilet paper, the parachute concept, the hot air balloon concept, and the mechanical winnowing fan all appear in the Chinese record centuries before they appear anywhere else. The magnetic compass was first described in China in the 11th century of the Common Era as a navigational tool for ships and reached Europe and the Islamic world within 2 centuries. Its effect on navigation was transformative. Without the compass, the great age of European maritime exploration that began in the 15th century would have been considerably more limited and considerably more dangerous. Chinese silk production, which the Chinese guarded as a state secret for centuries under penalty of death for anyone who revealed it, was the foundation of the Silk Road trade that connected China to Rome and carried ideas and goods across the length of the Eurasian continent. The secret of silk production was ultimately carried out of China in the 6th century of the Common Era, according to one account, by Byzantine monks who smuggled silkworm eggs out in hollow walking sticks. The range and the depth of Chinese technological innovation across the ancient and medieval periods is genuinely humbling. The civilization that produced paper and printing and gunpowder and the compass was also producing cast iron and mechanical clocks and magnetic compasses at times when the rest of the world had not yet thought of them. The reasons why the Industrial Revolution happened in Britain and not in China, when China had so many of the necessary technologies centuries or millennia earlier, is one of the most debated questions in the history of technology, and the answers that historians have proposed are varied and contested and still not fully resolved. What is not contested is that the technologies were there. China had them. The world eventually received them. And the world was changed by everyone. The ancient Nabateans built a city in a desert by mastering water. The city of Petra in what is now Jordan is famous today for its extraordinary rock-cut architecture. The rose-red facades carved directly from the sandstone cliffs that make it one of the most visually astonishing places in the ancient world. But the most impressive technical achievement at Petra is not what you can see from the photographs. It is what is hidden in the rock. Petra sits in a desert. Annual rainfall is minimal and unpredictable. The surrounding landscape is dry and harsh, and yet at its height in the 1st century of the Common Era, Petra had a population of around 20 to 30,000 people and supported the enormous caravans of the spice trade that passed through it on their way between Arabia and the Mediterranean. The Nabateans achieved this in a desert by developing one of the most sophisticated water management systems of the ancient world. They built cisterns cut into the rock throughout the city and in the surrounding hills to collect and store every drop of rainwater that fell during the brief rainy season. They built a system of terracotta pipes that carried water from springs in the surrounding mountains into the city through the narrow gorge called the Sick that was the main entrance to Petra. They built settling tanks to clean the water before it entered the distribution system. They built overflow channels to manage flash floods that could otherwise destroy the city in hours. The entire water system was engineered to collect, store, clean, distribute, and control water with a comprehensiveness that allowed a large city to thrive in an environment that should have been able to support only a fraction of that population. The Nabatean water engineers were so skilled that they could calculate the catchment area of a watershed, the volume of water it would produce in a typical year, and the storage capacity needed to supply their population through the dry months, with an accuracy that only direct experience and careful observation over generations could have produced. They did not have hydrology as a science. They had hydrology as a practice, refined over centuries of living in the desert and learning from it what it would and would not provide. The lost technology of Roman roads and why they lasted 2,000 years. Roman roads are among the most famous engineering achievements of the ancient world, and their reputation for durability is entirely deserved. Many Roman roads built 2,000 years ago are still in use today, either directly or as the foundations of modern roads. The reason for their extraordinary durability lies in a construction method of considerable sophistication that was applied consistently across the entire empire. A Roman road began with a trench dug to the depth of the road's total construction, typically around 1 meter. The bottom of the trench was compacted and leveled. Then the road was built up in layers, each layer serving a specific structural purpose. The lowest layer, the statumen, consisted of large flat stones laid to provide a stable foundation. Above that, the rudus, a layer of smaller stones mixed with lime mortar that created a solid bonded base. Above that, the nucleus, a layer of concrete made from small stones, gravel, and lime mortar that formed the structural core of the road surface. Finally, the surface layer, the summa crusta, of fitted stone slabs or gravel, depending on the location and importance of the road. The whole structure was cambered, built higher in the center than at the edges, so that rainwater drained off the surface to ditches on both sides, rather than pooling on the road and weakening it. The depth of the construction and the quality of the materials meant that the road could bear the weight of heavy traffic, including loaded wagons and marching armies, without the surface deforming or the structure degrading. The lime mortar used in the construction hardened over time as it carbonated, becoming stronger and more rigid with age rather than weaker as modern bituminous road surfaces do. The Romans understood that a road was not simply a surface, but a layered structure in which each layer served the layers above it, and that the quality of the lowest layer determined the quality of everything above it. This understanding of structural engineering principles applied to road construction produced roads that lasted not because they were made of special materials, but because they were made with exceptional thoroughness. They were built right, and things that are built right tend to last. What it means that so much ancient technology was lost and then rediscovered. One of the most thought-provoking patterns in the history of technology is how often ancient knowledge was lost and then had to be painfully rediscovered centuries or millennia later. Greek fire vanished with the Byzantine Empire and has never been fully reconstructed. Damascus steel died with the craftsmen who made it. The Hippocaust was forgotten for over 1,000 years before underfloor heating was reinvented. Roman concrete was not matched for durability for nearly 2,000 years. The astronomical capability represented by the Antikythera mechanism did not reappear in European clockmaking until the 14th century. Chinese printing technology took 400 years to travel from China to Europe. These are not simply stories about information failing to travel. They are stories about the fragility of technical knowledge when the social and institutional structures that support it collapse. Technology does not exist in isolation. It exists in a context of materials suppliers and trained craftsmen and institutional support, and economic demand and accumulated practical knowledge that lives in the hands and the minds of practitioners rather than in books. When that context is disrupted by conquest or economic collapse or political change, or the simple death of practitioners, the technology can vanish even if the physical examples survive. A Roman concrete harbour wall is still standing in the Mediterranean, but for 12 centuries after the fall of the empire, no one could make concrete as good as it, because the knowledge of how to make it was not in the wall, it was in the people who made it, and those people were gone. This fragility of technical knowledge is one of the most important lessons the history of technology teaches. The things we know how to do are only as secure as the people who know how to do them, and the institutions that support and transmit that knowledge. Every skill that exists only in a small number of living minds is a skill that is one generation away from being lost forever. The ancient world lost many things it could have kept. We are fortunate that it lost as few as it did, and we would be wise to pay attention to what we ourselves might be in the process of forgetting. The ancient world's relationship with metals was more sophisticated than textbooks suggest. The standard story of ancient metallurgy runs from the Stone Age through the Bronze Age to the Iron Age as a neat progression of increasingly sophisticated metals. The reality was considerably more varied and more interesting. Different cultures developed different metallurgical traditions that were in some cases more advanced than the standard timeline suggests, and in other cases skipped steps that the timeline implies were necessary. The ancient Andean cultures of South America were producing extraordinarily sophisticated metalwork in gold, silver, copper, and bronze from at least 2,000 years before the Common Era. Their techniques for working gold, including hammering, annealing, alloying, and surface enrichment processes that allowed them to produce objects with a pure gold surface over a copper or low-grade gold core, were of a sophistication that astonished European metallurgists when they first encountered the object of the Spanish conquest. The tumbaga alloy, a mixture of gold and copper developed by Mesoamerican and South American smiths, could be treated with acidic plant juices to dissolve the copper from the surface layer, leaving a film of nearly pure gold on an object that was substantially cheaper than solid gold to produce. This depletion gilding process required an understanding of the differential chemical behavior of gold and copper in acidic conditions that was empirically derived, but chemically sophisticated. In sub-Saharan Africa, iron smelting was developed independently of the Near Eastern tradition, and the iron working traditions of Central and West Africa produced tools and weapons of considerable quality from furnaces of sophisticated design that achieved temperatures high enough for smelting through ingenious use of natural wind and forced air bellows. The Haya people of Tanzania were producing medium carbon steel in preheated forced draft furnaces around 2,000 years ago, using a process that would not appear in Europe until the 19th century. The history of metallurgy is not a single story unfolding from a single origin point across the globe. It is many stories, developed independently in many places, each producing its own innovations and its own peaks of sophistication. The metals of the ancient world were worked by people who understood their materials through generations of practice, and whose achievements, when examined carefully, consistently exceed what the simple narrative of progress from primitive to sophisticated would lead us to expect. The secrets hidden in ancient plants and how ancient peoples used botany as medicine and technology. The knowledge of plants and their properties that ancient peoples accumulated over thousands of years represents one of the most extensive and most practically valuable bodies of empirical knowledge ever created. Before chemistry existed as a science, before pharmacology existed as a discipline, human beings were using plants to treat illness, to preserve food, to produce fibers and dyes and building materials, to create poisons and antidotes, and to achieve effects ranging from pain relief to infection control to surgical anesthesia. The Ebers Papyrus from ancient Egypt, dating to around 1550 years before the Common Era, contains over 800 plant-based remedies for a wide range of conditions. Many of the plants it recommends have since been shown to contain compounds with genuine medicinal properties. Willow bark, recommended for pain and fever in multiple ancient medical traditions, contains salicin, which the body converts to salicylic acid, the same compound that aspirin is derived from. Opium poppy, used as a painkiller in ancient Mesopotamia and Egypt, contains morphine and codeine, still among the most effective pain-relieving compounds known. Artemisia, a plant used in traditional Chinese medicine for over 2,000 years to treat fevers, including what we now recognize as malaria, contains artemisinin, which was identified in the 20th century as one of the most effective anti-malarial compounds known, and which earned its discoverer Tu Youyou the Nobel Prize in Medicine in 2015. Tu Youyou was guided to artemisinin in part by reading ancient Chinese medical texts that described the use of artemisia for fever. The ancient knowledge pointed the modern scientist toward the modern discovery. The botanical knowledge of ancient peoples was not superstition dressed as medicine. It was empirically derived knowledge of genuine value, accumulated over thousands of years of careful observation of which plants helped, which harmed, and which conditions they affected. Modern pharmacology has validated a significant proportion of traditional plant medicine, while rejecting other parts as ineffective or harmful. but the proportion that has been validated is large enough to demand profound respect for the empirical tradition that produced it, the engineering of ancient temples, and what it tells us about structural knowledge. The great temples of the ancient world were not simply religious monuments. They were also engineering achievements that pushed the limits of what was possible with the materials and techniques available, and that incorporated structural knowledge of considerable sophistication. The Parthenon in Athens, completed in 432 years before the Common Era, is famous for an optical refinement that reveals the depth of understanding its architects brought to the project. A perfectly straight building at the scale of the Parthenon would appear to sag in the middle when viewed from a distance because of the way human visual perception processes horizontal lines at large scales. The architects Ictinus and Callicrates corrected for this by building the Parthenon with a very slight upward curve, a convex distortion called entasis, in its horizontal surfaces, and with columns that are slightly thicker in the middle and that lean very slightly inward toward the center of the building. These adjustments are so subtle that they cannot easily be seen by someone looking at the building in person, but they produce a building that looks perfectly straight and regular when viewed from normal distances, because the slight irregularities introduced into the physical structure cancel out the apparent irregularities that human perception would otherwise introduce. The mathematics required to calculate these corrections and the craftsmanship required to execute them consistently across a building of this scale represent architectural and engineering practice of extraordinary refinement. The temples of ancient India showed different but equally sophisticated structural knowledge. The interlocking stone systems used in some Hindu and Jain temples produce structures that are held together by the weight and interlocking geometry of the stones themselves without the use of mortar. The stability of these dry stone constructions at heights of 30 or 40 meters required an understanding of load distribution and structural dynamics that was entirely empirical in its origins, but entirely reliable in its results. These buildings are still standing. Some of them have survived earthquakes that destroyed more modern structures around them because they were built right, by people who understood, through experience and observation, what right meant.